the points are really important. In the worst case, the simplex method is also exponential complexity, meaning in the worst case, the simplex method would need to explore all possible vertices. You can imagine that as if we would maximize in this direction, and this would be the optimal solution. Actually, what we would find is a path which would be going like this. Okay, so exploring or visiting all vertices before finding the optimal one. Okay, yeah.
Does it guarantee progress?
Yeah, it does. Okay. If you don't cycle, which you may, then yes. And yes, you could start cycling. So the correct answer would be no. In general, it does not guarantee convergence. And I guess I will mention it in the subsequent lecture, like how do we see that this kind of cycling has happened and what to do against it. So let me wrap up how the algorithm really works. So this is a more general formulation. So we have now split the constraints into individual ones. And what the algorithm does, it first creates the initial simplex tableau. So step number 0 would be convert your problem into this form. Maximize and all equality constraints with non-negative variables. Then step number 1, create the simplex tableau. The simplex tableau is basically already written here. The rows are the coefficients in front of individual decision variables in corresponding constraints. And the final column is the right-hand side of the constraint. And then the last row that contains minus values of these price coefficients in the cost function. Okay. So form the tableau, then identify whether the solution is not optimal. Very often, just by forming this initial tableau, you already find the optimal solution. So it might be that already the initial condition, the initial solution is optimal. If it is, abort. If it is not, pivot. Okay. For that, we need to select the pivoting variable. We know how to select the column as the smallest negative entry in the last row. And the row position we select as the smallest positive ratio between the right-hand side and the corresponding leading coefficient. And then, yeah, that's what's written here. And then we pivot using elementary row operations. And actually, probably, or at least you hope that you would never do this by hand, but you could. Okay? Probably in the exercises you could do at least a small example, because it's really, I mean, you have to get used to how the software does it. So the software, what it does now, it performs these pivot operations, checks optimality, and repeats all over. Okay? And fortunately, as I said, I mean, it would be nonsense to solve this problem by hand, even though it could be, and that's what Danzig was probably doing initially. I mean, he was solving these problems when he had hundreds of decision variables and maybe hundreds of constraints, so those tableaus were really huge. But nowadays we have software to do that, and in MATLAB we have LimProg, which solves the linear programming problem. It's a solver which is included in the optimization toolbox. It implements 3 methods to solve these problems. One of them is the simplex method. And the input format is exactly this, so we have to have the minimization of the objective function. So again, what LimProg expects is just these data, C, A, B, A equality, B equality, and lower upper bound. It is your responsibility to convert your problem into this standard form. So if your problem is maximize something, first you have to add negative entries or multiply the C by -1 to make it a minimization problem. So we have minimization of the linear objective function, then we have inequality constraints, equality constraints, and lower upper bounds on the optimization variables. And then you could use different syntax. So if you just want to minimize the objective function subject to inequalities, as the first input you provide the vector of C's, which multiply the decision variables in the cost function, and then A and B for the constraints. Again, if you have maximization, Actually, all you need to do is to put minus in front of the C. If you have equality constraints, you can provide them here, and if you have even lower and upper bounds, you can provide them there. If you have a problem which has no inequality constraints and only equality constraints, so you would like to use this formulation, put these as empty matrices. That tells limprog that you have no inequality constraints and you have equality constraints. So in other words, don't do this. Don't just remove that, because that would make limprog think that these are actually inequality constraints. And then limprog yields 3 output arguments, as you are probably familiar. So we have the vector of optimal decision variables as the first output. We have the value of the objective function and the status, which says whether the solution was optimal or whether maximal number of iterations was reached. Again, the simplex method could get into cycling, and we will cover that on the next lecture. So that's being indicated here. It could be that the problem is infeasible, meaning there is no solution to your problem, or it could be that the problem is unbounded. And we will see graphical examples of infeasibility and unboundedness on the next lecture. So this pretty much wraps what I wanted to share with you today, and I would like to thank you for your attention and take any questions if you have any.